Okay, in the next part of the notes, we want to move into our discussion of infinite series. And so just a couple of definitions to revisit from section 9.4. Convergent series is a series that has a sum or a limit, meaning that when you add up infinitely many terms in the series, it converges or settles down on a number. And you might think, well, how is that possible? How could I add up infinitely many numbers and it settle down onto a specific number? Well, I'm not necessarily saying that it's going to equal that number ever, because I'm never going to be able to add up infinitely many terms. That's just impossible. Nobody has an infinite amount of time to do that. So what we say instead is that it converges to that number, meaning we can get it as close to that convergent number as we could possibly want, as long as we take enough terms. And so hopefully that's making a little bit of sense. Basically, if that doesn't happen, then you're talking about a divergent series, meaning a series that does not have a limit. Essentially what's going to happen there is that the series is going to increase or decrease without bound. And so infinite arithmetic series are always divergent. They're always divergent because they always either increase or decrease without bound. And again, I want to emphasize that we're talking about infinite arithmetic series as opposed to finite, which we did earlier in the notes. And so if the series is arithmetic and it's infinite, it diverges, end of story, point blank, period, you're done. If the series is infinite geometric, it depends on what the ratio is. If the series has a ratio that is greater than or equal to 1, then the series diverges. Otherwise, if the ratio is smaller than 1, then the series converges, and more specifically, we can say that it converges to the number that's given by a sub 1, which is the first term, divided by 1 minus r. Okay, so now that we've kind of discussed when a series converges or diverges, let's see if we can work some examples and determine the convergence or divergence of these three series. So starting with A, we've got 2/3 plus 1/3 plus 1/6, etc. And the first thing we want to do is figure out, is this particular series A or G? And what I mean by that is it arithmetic, meaning it has a common difference, or is it geometric, meaning that it has a common ratio? And so if this series is arithmetic, then what that means is that it would have a common ratio. And so I'm just going to check that real quick. If I take any term and I subtract the previous term, that should be the same number no matter which two terms that I choose. So if I have 1/3 minus its previous term of 2/3, then that is going to give me a ratio of -1/3. Now, if I take the next term after that, which would be 1/6, and I subtract the previous term, which is 1/3, this is going to give me -1/6. And notice that these two differences do not match up, and so therefore this is not an arithmetic series. Okay, so is it geometric? Well, we need to just double check that by seeing if there is a common ratio. So now, is it geometric? Well, that means that I would take any term and divide by the previous term, and that's going to give me, in that particular case, if I do 1/3 divided by 2/3, that will give me 1/2. If I take 1/6 and divide by 1/3, that is also going to give me 1/2. And so I notice that this series is geometric, and more importantly, it is geometric with a ratio of 1/2. And from the previous set of notes, we know that that means that this series will converge. And so that's what we will say here. This infinite geometric series will converge since that ratio is smaller than 1. Okay, letter B, -4 minus 2 minus 0 plus 2 plus 4 plus 6 plus 8. You probably get the idea. This one is actually pretty easy to determine that it's arithmetic, but again, just what did we previously do? Took any term and subtracted the previous term, and so that gives you 2. And then if you take 0 and subtract the term before it, that also gives you 2, which means that this series is arithmetic. And more importantly, it is infinite arithmetic because of the plus ... here. And so what we're going to say is that because of those two facts, this series diverges, and I'll just be a little bit more descriptive here. It diverges because it is infinite, and more importantly, it is infinite arithmetic. Okay, letter C, you first of all want to determine, is it arithmetic or geometric? So if it's arithmetic, that means if we take 3 minus 1 and 9 minus 3, we ought to get the same number. And notice that we do not get the same number. Therefore, this is not arithmetic, which leads me to believe that it could be geometric. By the way, not every series has to be arithmetic or geometric, but that's what we're going to focus on here in this pre-calculus course. And so you can pretty much just be guaranteed that in this class, we'll either be talking about arithmetic or geometric. So if I take 3 and divide by 1, that gives me 3. And if I take 9 divided by 3, that also gives me 3. And so I notice that this is geometric with a ratio equal to 3, which is larger than 1, which means that this infinite geometric series is going to diverge by definition, since the ratio is larger than 1. Okay, so before we get to our main entree of determining if a geometric series converges or diverges, let's first talk about how to find partial sums. And so the partial sums are just basically what they say. They are partial sums of the series, meaning you're only adding up the first however many terms. And so the first 5 partial sums, the very first one for this first example would just be the first term only. And so that's going to be 0.1. The second partial sum will be the sum of the first 2 terms, so 0.1 plus 0.01, which will give me 0.11. The third partial sum then will be 0.1 plus 0.01 plus 0.001, which will result in 0.111. Probably at this point you can see what's happening here. S sub 4 is going to be the sum of the first 4 terms, and so that would be basically the third partial sum with 1 additional term added to it, and so that's going to be 0.1111. And so finally, what is the fifth partial sum? That's just going to be point and then 5 ones. And so my first 5 partial sums, if I were to write them in set notation, would be 0.1, 0.11, 0.111, 4 ones, and then finally 5 ones. And what do you think this converges to? Or do you think it converges? Well, hopefully you see that this sequence of partial sums is converging, in this particular case, to 0.1 repeating. And so 0.1 repeating is just the fraction 1/9. And so this particular series is going to equal to, or sum up to, 1 divided by 9. Now, in letter B, we could do the same thing. S1 would just be the first term. S2 would be the sum of the first 2 terms, so that would be 30. S sub 3 would just be the previous partial sum plus the next term, and so that would be 60. The fourth partial sum would be the previous partial sum plus the next term, which would be 40, and so that would equal to 100. And then S sub 5 would be 100 plus the next term, which of course would be 50, and so this would be 150. And so my partial sums are going to be 10, 30, 60, 100, and 150, and then we could keep going if we wanted to, but what we're going to see is that this sequence of partial sums does not have a limit. It's going to continue to increase without bound, and because of that, we say that the series diverges. And so that should make a little bit of sense, I hope, because if you look back at the original series, this is an arithmetic series, But even more specifically, it is an infinite arithmetic series because of the plus ... here. It just keeps going on and on and on and on. And so remember from the previous slide, we said that all infinite arithmetic series diverge, and that's exactly what we were able to see through the first 5 partial sums. Okay, one more example of partial sums, and so the first partial sum here would just be the first term, which would be 1. The second partial sum will be the sum of the first 2 terms, which would be 0. The third partial sum will be the sum of the first 3 terms, which will be 1. The fourth partial sum will be the sum of the first 4 terms, which again will be 0. And the fifth partial sum will be the sum of the first 5 terms, which will be 1. And so your first 5 partial sums are 1, 0, 1, 0, and 1. And you can see that while those aren't increasing or decreasing without bound, they're also not approaching one particular number. This sequence, sequence of partial sums is bouncing back and forth or oscillating back and forth between 2 different values. And so any sequence that is oscillating, we say that it diverges. And so this sequence of partial sums diverges, therefore this series also diverges. It will not settle down on one sum whenever you add up infinitely many terms.